So this is the beginning of the liquid, solids, and solutions unit. So we're going to talk about the properties of liquid solids first, and then we'll head into intermolecular forces. So first, let's talk about liquids and some properties of those liquids. Now, you have to remember that gases, liquids, and solids are obviously different from each other, but liquids have three properties that govern all liquids, regardless of what type of liquid we're talking about. Now, if you remember back to when we talked about gases, gases were had no definite shape, no definite volume, and they were easily compressible. Now, so for liquids, we're going to have they have no definite shape. We know that because, well, if you put 2 liters of If you take 2 liters of soda and dump it onto the table, it's not going to look like a soda bottle anymore. It'll just spread out into a big blob of soda. So it has no definite shape. But it does have a definite volume. Let's erase no. And again, I know this because if I take 2 liters of soda and pour it into a 1 liter bottle, I will overflow the bottle because I still have 2 liters of soda. Whereas opposed to the gas, if I took 2 liters of gas, I can compress that 2 liters of gas down to 1 liter if I really needed to. But I cannot do that with liquids, which brings me to my next point, is they are not compressible. So, and you know this, anytime you've ever done a cannonball into a pool, you know immediately that liquid is not compressible. Because when you hit that water goes everywhere, splashes all over the place. Because if it was compressible, when you hit that water, it would just compress down underneath your body, and you would sink into the gas, into the liquid. But because liquids are not compressible, they spurt out all over the place. One of the major issues too with that, the points about that is if you've ever seen like a Valvoline or a Pennzoil ad, you know, a car oil ad, they talk about its lack of compressibility in there, that it does not shrink down so that it can easily coat everything. While I'm talking about Pennzoil and motor oils, you'll also have talked about you've also heard the term viscosity. Viscosity is a liquid's resistance to flow. That's a key point right there, is the fact that it's resistant to flow. Motor oils do not want to flow. You do not want it to flow like water. Water has a low viscosity. It flows everywhere. But motor oil does not. It has very high viscosity. And the reason they want it to have a high viscosity is they want it to stick to the engine parts. They want it to coat everything and stay on it at all times. So you want high viscosity with things like with things like motor oils. Molasses also, you want high viscosity. You know, and other things, maple syrup, honey, all have high viscosities. And finally, the last property of liquids, which applies to only liquids, is something called surface tension. Surface tension is how strong the forces between the molecules at the surface of the liquid are. So if you've ever seen those water striders, they're the tiny little bugs like on the edge of a lake or a stream or something, and they zip along and they just bounce along the top of the water and they never actually sink in. That is the water strider exploiting the surface tension of the water. Or maybe back in middle school, you've done the how many drops of water fit on a penny, and you get that big bubble of water going on top of the penny. That's surface tension. It's how much the molecules want to cling to each other at the surface, and it becomes, water has great surface tension, very, very high. That's also why, believe it or not, if you've ever done a belly flop, that's the reason belly flops hurt, because when you hit that water, its surface tension actually increases. So they say that if you jump, like if you do bungee jumping or something like that over water, and the bungee didn't bungee you, and you hit that water, it's like jumping out of a 2-story building onto a parking lot, a concrete parking lot. That's how bad it can hurt your body. So it can actually break bones. So I digress. So here's a little video. I've got the sound is not important here, but I'm going to show you something which is called a non-Newtonian fluid, and it's a little demonstration of what happens with liquids. So here's a guy running, and let me back it up a couple of seconds. Okay, so this guy is going to run across this little pool. Now this pool, and you've probably done this again in middle school, is the cornstarch and water pool. So you fill the pool with cornstarch and water, and now what makes this special is, even though it's a liquid, when he pounds down and he exerts a force on it by running on it, you could see that it actually bounces back more like a solid does, sort of like a bouncing like a trampoline or something. Okay, and the other guy ran right across, and when he exerts the high pressure of his feet onto that surface, it hardens up and he can run across it like it was running across a trampoline. But when the other guy stopped putting pressure on it and just stood still, look what happened. He sank down. You can see as the guy moves his arms back and forth in the water, it toughens up and it becomes more solid. But when he stays still, it's very liquidy. So if you've ever done this in middle school, you'll notice if you touch it, it feels like water, but you hit it hard and it feels like a solid ball. So that's a good example of how you can manipulate the properties of liquids. Okay, now let's talk about the properties of solids. Again, solids have three properties. Now solids are much easier because solids have a definite shape. A desk will always look like a desk. They have a definite volume. The desk will always be the same size. No matter what room I put the desk in, it will always be the size of a desk. Now, this last one is a little bit different. And the reason this one's a little bit different is we don't normally think about solids like this because it's kind of more of an obvious thing. Solids do not flow. Now, liquids flow. Now, flow means like movement down a surface. So a gas, I can actually pour certain gases down ramps and things, and I will do that demo. I've done that demo in class, where I can pour a gas down a ramp because it's more dense. I can pour a liquid, obviously, down a ramp. Liquids always like to flow, but solids, I can't pour a solid down a ramp. Unless it rolls or it slides, but it doesn't flow. Like if I put a block on a ramp, that block will stay there forever, unless the force of gravity pulls it down, and then obviously it'll slide down, but it doesn't actually flow. So this is key with solids, is they do not flow. Very, very important there. Okay, and that's all we're going to do about liquids and solids properties. Now let's talk about intermolecular forces real fast. Okay, an intermolecular force is an attraction between molecules. Okay, hence the reason it's called an intermolecular force. Now it's between the molecules, and it means two or more molecules are going to be having these attractions to each other, which are going to hold themselves together. There are three intermolecular forces we're going to talk about. The first is dispersion force. Dispersion force is the weakest type of force. It exists in all molecules, regardless of what type of molecule it is. It's going to be there. Intermolecular forces are caused by these very weak attractions due to partial charges on atoms. So think about an atom, if you will. You have your protons and neutrons, and you have your electrons flying all around, all over the place. Okay. Now, because these electrons are basically moving in random patterns, they're not circulating like on an orbit. Sometimes the electrons are closer to one side. Sometimes they're closer to the other side. Now, when they shift closer to one side, it creates a slight negative charge on one side and a slight positive charge on the other. This is these partial charges. Okay. So but think about it. Electrons are constantly moving. So they move towards one side for 1 second, and then they quickly shift to the other side. So this partial charge is constantly moving back and forth and back and forth and back and forth. Okay, and that's what's creating these dispersion forces. Now here's the thing. The more of these partial charges you have, the stronger the intermolecular force will be. So heavier and longer molecules have stronger forces. Okay, so things that are long chains will have a stronger force. Best example I can give you of this is propane versus octane. Propane, we know, is the stuff that's in barbecue, is in those white canisters, like the blue Rhino canisters underneath your barbecue grill. Propane has 3 carbons and 8 hydrogens coming off of it. All those bonds that don't have an H are hydrogens. Octane is the stuff that's in gasoline. 5, 6, 7, 8. 1, 2. Okay. And it has 18 hydrogens coming off of it. This substance is a gas. This substance is a liquid. Okay? Do they have different properties? Not really. except for the fact that there's a whole lot more over here than there is over here. Okay, so this tiny little molecule here has very, very weak attractions, very weak dispersion forces, and because of that, the molecules do not hold themselves together, and the molecules can fly off as gas. But because in the octane molecule, there are stronger molecules, because not only is it heavier, but it is much longer. It has now all of these different, it can make a partial charge here, and 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 here. Okay, all those places can have partial charges, so all those places could form dispersion forces, and therefore now it's a liquid. And that's really what defines a gas, a liquid, and a solid, is their strength of intermolecular forces. Now let's talk about dipole forces. Dipole forces occur because of polarity. Okay. Now remember, in polarity, you're talking about a situation where there's not a partial charge, there's a permanent move of the electrons towards one side. So it's no longer the fact that the electrons are shifting back and forth and back and forth. Now they have pushed towards one side because one thing has a stronger electronegativity than the other. Okay, so I wrote caused by a permanent charge shift. So, for example, HCl, LiBr. Both of these have big electronegativity differences. Because there's a big electronegativity difference, the electrons shift towards one side permanently, and that side will always have a slight negative charge. The opposite side will always have a slight positive charge. And lastly is hydrogen bonding. Now, hydrogen bonding is a very, very strong dipole force. But hydrogen bonding is very specific as to what type of dipole force it is. The key with hydrogen bonding, and now remember, this is still an IMF, okay? Not a bond. People mess this up. Okay, before I move on, people mess this up. They see hydrogen bonding and they think it's the same as like a covalent or ionic bond. It is not. It is just an intermolecular force. It is an attraction between molecules. Okay? It is the strongest intermolecular force, and it only occurs when you have a hydrogen attached to a nitrogen, an oxygen, or a fluorine. I'm sorry, it's when the H is attracted to a nitrogen, oxygen, fluorine, and that atom has a hydrogen on it also. Okay, let me give you an example. My example from up above. HF is an example of something that will have hydrogen bonding. LIF is not. Even though LIF has a fluorine, it does not have the hydrogen attached to it. Because it has a lithium, this will not have a hydrogen bond. No H bond. Okay, this, because of the large electronegativity difference, will have dipole forces as its primary force. Okay, so again, both of these are between polar molecules. Okay, so B and C are basically the same, but hydrogen bonding is just more specific. We will use these intermolecular forces more when we talk about solutions and why one thing dissolves in another.